In this video, we'll talk more about the theory of second-order linear differential equations. So just like first-order equations, we have existence and uniqueness theorems for these equations as well. What we'll focus on here is the one for linear equations. So if we have a second-order linear non-homogeneous or homogeneous initial value problem of the form here, y double prime plus p of ty prime plus q of ty equals g of t, with two initial conditions stated here. As long as all three of these functions, p and q and g, are all continuous on some open interval that contains t0, this initial condition value here, then the solution I know exists and has a unique solution on this interval I. This should be very reminiscent of the theorem that we had for first order linear equations. It's the same sort of idea. As long as all these functions are continuous, I have a solution, I know it exists, I know it is unique. And I can determine intervals of existence by looking for where the discontinuities are of these three functions and expanding out from t0 to get to them. Problems of this type work identically to the ones that were of the same form for first order equations. So that means that as long as I give you an initial condition in the form of the value of the function in this derivative at a given point, and things are continuous, then we know the solution exists and is unique. Now that we have this idea, we can talk about the idea of a fundamental set or a basis of solutions to a given problem. So we say that two solutions, y1 and y2, form a fundamental set of solutions to the differential equation, the homogeneous version here, if the set of all linear combinations, c1y1 plus c2y2 for different values of c1 and c2, contains all solutions to the differential equation. Now note that by taking c1 to be 0, 2 to be 1, and vice versa, this y1 and y2 must already be solutions to the differential equation. But what does this mean? Well, this really means that this linear combination here can meet all initial conditions at a given point. Why does that work? Well, that's just because I know solutions are unique if I specify an initial condition. So if this linear combination can meet every initial condition, that's the only thing left to define a different solution to this equation is the initial condition. So once I can meet all of them, I know this will generate all possible solutions as long as I can meet every initial condition, because the solutions are unique. I can't get two different solutions with the same initial condition. So as long as I can meet any possible initial condition, I've generated all solutions. Which means the idea of fundamental set also means meeting all initial conditions, which gives a better expression for calculating this out. So this happens when y1 at t0 times y2 prime at t0 minus y1 prime at t0, y2 at t0 is not 0. That gives us enough information to solve out for the c1 and c2 to meet the given initial condition that we want to solve for. So as long as this is not 0, then I can meet any initial condition that I want at the point t0. This is another definition to use for this fundamental set of solutions. So if this property holds for a given pair of solutions, then they will form a fundamental set, which means that I can take a linear combination of those two solutions and get to any solution that I want for this differential equation with any initial condition that you give me. The initial terminology in this regard, so if I have two solutions, y1 and y2, to a linear second order homogeneous equation, then we define this function w. This is a more theoretical idea, but we'll state here anyway. This function w as a function of t to be the function y1 of t times y2 prime of t minus y1 prime of t times y2 of t. And this is called the Wronskian of these two solutions. What you should recognize is that if I plug in t0 here, I get the exact same formula from before for what I want it to be not 0 to make sure I could solve any initial condition. And furthermore, we say that two solutions, y1 and y2, are linearly independent if their Wronskian is non-zero. These are all really ways to talk about the same thing, to talk about this idea of a fundamental set or a basis of solutions, meaning that these two solutions here can generate all possible solutions of the initial value problem provided they meet one of these conditions, either linearly independent, the Wronskian's non-zero, that expression there is not zero. All those things are equivalent to say these two generate a fundamental set of solutions, and I can meet any initial condition that I want with a linear combination of these two solutions. Now, one other theoretical statement that I'll mention here to illustrate more how this works is what's called Abel's theorem, and its point basically says that for any solutions, we either have that the Wronskian is always zero for all t, or it's never zero. So either this function is identically zero forever, or it's never zero. It can't like cross t at one point. Which means to check if things are linearly independent, you don't have to check at one point. If at that one point it is non-zero, you know they are always linearly independent. And if at one point it is zero, you know it's always zero and they are linearly dependent, and that this does not work. So that is more of the theory behind second order equations and how these things come about, which is going to be important as we go to figuring out when do we have enough information or the enough solutions to generate all possible solutions of this problem. Because we want to be able to generate all of them to make sure we get the right one that can meet the initial condition that we're looking for a given problem.